All right, some vector questions are always a bit troubling, so let's try doing a few. A journey consists of two displacements. The first displacement is 500 meters northerly direction, and the second is 200 meters easterly. So someone is going 500 meters north, then he goes 200 meters left. Oh, sorry, right? Easterly, east is right. Okay. Okay, in the space below, I need to draw this out. And first I want to do is select the scale of your diagram. Okay, I'll do that in a minute. On the diagram, show the displacement and the resultant displacement. Show the two displacements. Well, the ones in green I've already drawn, but neater. And the resultant. Okay, we'll do that at the end. Determine the size and magnitude and the direction of the resultant displacement. All right, let's do this. All right. So first things first, what do I want to do? I want to take my first vector and first, actually, I want to come up with my scale. I cannot draw um, 500 meters on this piece of paper, right? So that's an impossible task. So what do I do? So I'll set up a scale. What is my scale? Well, I'll assume my 1 centimeter of my scale is equal to 100 meters, right? What does that mean? Well, if I'm over here, and if I have my scale over here, I'll need a second to draw it, right? On second thought, let's make it a little lower. I'll need some space. Okay, that's my dot. And I'm gonna move 500 meters up, and that's the first displacement. 500 meters like that. Now, 500 meters for me on my scale of my choosing, I could have gone with any value, but I mean, I want to keep it simple. I've kept 1 centimeter as 100 meters, so I'll have to draw a line that's going up by 5 centimeters. So let me do that in a second. All right, pretty cool. All right, you can see it's 5 centimeters to the north, or 500 meters if you want to extend your imagination. All right, 1, 2, 3, 4, 5. Okay, we're done here. Now the second part of the question is I need to draw a easterly, as they said, line that is 200 meters like that in that direction, easterly direction. So someone moves up by 500, then, or north by 500, towards the right by 200. That's pretty cool. So, and I've done it. All right. Do I really need to draw arrow tips over here? I can if I want to, maybe right at the end, but notice what the next part of the question is. I have to find out the resultant magnitude. So what we've done is we've kind of drawn the two vectors out. I'll just draw this because it looks nice. We've drawn the vector out. Now the resultant vector is going to be, well, this vector, right? So we could calculate it, that's fine, but because they want us to solve it geometric, like using geometry, right? To measure it out. So let's measure it out and then apply the scale. Whatever the value comes out, let's say it comes out to be 9 centimeters. Does that make sense? It's going to travel 900 meters, right? In real life. Whatever this length is, if I convert it back into meters, and what's the conversion? Whatever this number is, that times 100 will give me my resultant vector, right, of these two displacements. So what I need to do right now is keep a scale at this point and the other point matches this point and draw a line essentially and measure it and write down its measurement. So let's see if we can do that. All right, here's my vector drawn and my measurement comes out to be, I measured it, you can see it's very close to 5. And that's 5 and slightly more. That slightly more is 5.4 centimeters. So this length is actually 5.4 centimeters that way. Okay. Now, it's not rocket science where if this length is 5 centimeter actually drawn, but it represents 500 meter, right? And and that's 2 centimeter, and that represents 200 meters. So 5.4 centimeter means how much did the object get displaced? Well, the difference is of 100. So that'll lead to 540 meters of displacement. Uh, yeah, and what you can actually do is calculate it as well, just to check if you're getting the right answer or not. And it's unlikely you'll get an exact answer because you're drawing it out, but you can use the Pythagoras theorem. 200 square, 500 square, add them up, square root. You'll get a value very close to this value. All right, let's see what's required, what else is required. So they want us to give us the scale. What scale did I end up using? Well, I said that I wanted to use, and you're a little free. This isn't the most scientific thing in the world. You're a little free to say what you want and how you want to say it. So I'll just say my 1 centimeter on this page is equal to 100 meters in real life. If you had said something like this, 100 meters is 1 centimeter, or if you had different values, that would have been fine, right? Or you could have just said 1 centimeter is 100 meters. That's also fine. All right, size. The size of the magnitude, we just calculated it, figured it out right here. It's 540. What's the direction? And we don't have to be very strict over here. A general direction is fine for this answer. It is in the northeastern direction, so northeast. All right, let's move on. Another journey covers a distance of 700 meters. Describe how it's possible that this journey has no resultant displacement. Any journey that has no resultant displacement means you have, someone moved there like that, there like that, there like that, and they're eventually back to where they started. So the net displacement is zero. They've moved, they're back where they began, right? So in this question, how do you answer that? Or another journey covers a distance. So a distance was covered by this much. Describe how it's possible for the journey has no displacement, right? It's the distance. So the total time covered or the total distance walked was 700, but they never say it's in the same direction. Well, that could happen when you walk 350 like that and then 350 back and your net displacement is zero. Or you could have gone in a circle as well, right? There's no strict rule. So as long as you stop where you started, you don't have a net displacement. So a very technical way, you can just say that in words, or you could just say in a slightly more technical way, if starting position is the same as your ending position, again, you could have said that in words, normal as a sentence as well, is same as ending position, no displacement took place. What is meant by velocity? It is the rate of change of displacement over time. All right. So let's zoom out a bit. Kind of like that. I think we're good. All right, what's going on over here? A boat travels from the area of still water into an area where the velocity of the water is 2 meters per second towards the northeast. So the water direction is given to us, right? We don't have to worry about all of these arrows. They're just giving us that this boat is in still water and it's moving, and eventually what's the word? Sailing, I guess. sailing over onto where the water starts moving, right? It's not stationary anymore. It's not still. So what's going to happen to the boat? Well, it's going to keep on going at 4 meter per second up, irrespective of whatever is happening here. But this water will add or push or give some velocity in that direction at a 45-degree angle. It'll do that, right? So it's not gonna, so this is 2 meter per second, so the boat won't start moving at 6 meter per second because the water is not pushing the boat along itself, right? It's kind of at an angle. So the boat will continue to move like this, and another velocity will be added to the velocity of the boat, kind of like that. So we'll do the head to tail thing, and I believe we have to draw it, so let's try doing it. But let's complete the question. Combining the initial velocity of the boat with the final velocity with the velocity of the water gives the resultant velocity of the boat. So they're literally telling us what to do. Take this vector, put it on top, and find the resultant. In the space on the page opposite, draw the vector diagram to show the resultant velocity. Use your diagram to find the size and direction of the resultant velocity. Now, you can do this question with a protractor, and that could help. You can also easily do it without one. Let's see how we can do that. All right, I'll put just a point for my starting point. And what I want to do is first get my velocity down. And over here, I don't care about the scale. They're not asking me. But what I'll do is I could take 2 centimeters as 1 meter per second. And this is a velocity diagram. Not that it changes anything. But I'll, just keep it true to what we did last time. 1 centimeter is 1 meter per second. Not that I have to write this, but yeah. So what I want to do is draw a 4 meter per second or a 4 centimeter line completely vertical with the boat, right? Or like the motion of the boat. All right, here's my vector, and I like the arrow. So I'll draw that, don't really need it. Now what I want to do is I want to make a 2 centimeter line like that, right? Now, again, you can use a protractor. That would be recommended. It'll save you some time. But what I can do is make just a quick right angle triangle over here, a square, right? And the idea behind it is that hypotenuse would be at 45 degrees, right? So you can do that, or if you don't have a protractor, or you can use a set square, just 45 degrees, right? Not a big issue. All right, what I'll do is I'll use a protractor. All right, here's my second vector, and you can probably see I'm misaligning it just a bit. It's better if I didn't do that, but oh well. It's a little difficult on the digital canvas. Anyway, that's the other thing. So which way is the boat actually moving now, right? Well, it's gonna give us, it will be given to us by the resultant. So now we have to put us one point of the scale here, the other point here, and just sketch a line, measure it, and we're kind of done. All right, I'm getting a value very close to, here's my vector, of course, and I measured it as well because when I was drawing it, it's 5.5 centimeter, right? And you could have drawn a bigger one. You could have actually used inches. Again, this number is important. So what did we say earlier? 1 centimeter was 1 meter. So 5.5 is 5.5 meter per second, right? Well, this was 4 meter per second, just to kind of label it properly. Not that it's required strictly. No one asked us to do it. And yeah, so what is the size of the resultant velocity? Let's move it a little down. The size, we just measured it. It is 5.5 meter per second, right? And direction, again, it's towards the northeast. State the difference between a scalar quantity and a vector quantity. That is easy. A scalar quantity has just magnitude, whereas a vector has magnitude and direction. All right, two examples of each type of quantity. What examples do we have? Force, sorry, we're talking about scalars, so speed, time, mass, whatever you guys prefer. Vector, acceleration, I want to say that, feel like it. Velocity is also fine. Force, of course. All right, the figure shows the directions of the size of the two vectors p and q. In the space next to the figure, draw the labeled vector diagram to show the resultant vector obtained by adding the vectors p and q. So that's kind of easy. What you want to do is grab a scale and keep it over here, find out the measurement. Now, for this, there are no angles or anything. You don't have to be too accurate. Just you essentially have to redraw it. So I'll just freehand it. I think that's what it's called. And that's my vector q. I'll also label it q. All right, then I want to take this vector and put it on top because we're adding them with the head to tail rule in mind. So that poorly drawn vector is vector p. All right, fair enough. What's going to be the resultant? Well, you started off here and you're ending there. So let's see if I can join that. That's not too bad. All right, so that's the resultant. It's not really asking us to label it or anything, but I think we will. Resultant vector. And yeah, all right, straightforward. Now your diagram will be a lot more neater if you used a scale, but you don't have to be too accurate. There's no angles or anything, just a general idea what the resultant would be like. Now again, we've seen this question many times, and if you take vector p first and add q to it, you'll still end up with the same vector, right? So it doesn't matter where you start as long as you follow the procedure in the correct fashion, you'll get the resultant as the same.